good morning, everyone. First of all, many thanks to the organizers, Reika, Anne, and Thierry, for this lovely conference. So I'm going to speak about basically deriving the doubly parabolic Keller-Segel system in the plane, so in R2, through a particle system, going from the particle system. And this is a joint work with Nicolas Fournier, who is at Sorbonne University. So first of all, I would need to kind of tell you about like what is the model we are interested in, and then we'll go to the probability to the particles and everything. Okay. So we're interested in the very well-known today and very famous model for chemotaxis, the Keller-Segel model. So it was designed in the 70s to model so this phenomenon of directed movement of a cell population triggered by a chemical stimulus. So you imagine cells moving randomly in their environment, and then they are attracted by some chemical signals, and then they start directing their movements towards the zones where the signal is very strong, and then they go there together. So it's a kind of auto-organization phenomenon. Okay, and they are also capable of emitting the signals when they are triggered. Okay, so this model was proposed to model the onset of cell agglomeration with the population of the slime mold. So it's an organism that is unicellular but becomes multicellular because of some conditions in the environment, and when it does so, it uses chemotaxis, so to kind of agglomerate and then push the membranes out and become one thing. So, so what happens here? We have two players. We have this population of cells, and then we have some chemical that attracts them. So we call it a chemoattractant, and we have its concentration. So everything is in R2. And what happens is that the cells diffuse, and then they drift in the direction of the gradient of the concentration of the chemical. So they go in the zones where there is more chemical. And the chemical itself, it diffuses, then it disappears from the system with some rate lambda. And then it is produced by the cells, and this is where you have the coupling. So the cells emit the chemical with rate 1, okay? And here you have many parameters to talk about, but basically the most important one is this one here. This is called the sensitivity. So it kind of tells you how sensitive is the population to the chemical. And as bigger as it gets, you get more quicker to the source of the chemical, okay? And it's going to be very important for the discussions. So keep in mind that that's basically in front of the drift, okay? Then you have, there is no reason for these two guys to diffuse at with the same coefficients, okay? So you can rescale this. So you can the ratio basically between the two scales of the diffusion is here, okay? And then everything else is well, this can be 0. So on the first read, we can even set it to 0, okay? And what's important, okay, is that the first equation is a Fokker-Planck equation, preserves mass. So there is no birth and death of your cells at this point, like, okay? So the mass is constant, and for us, the mass is going to be rescaled to 1, okay? Because we work with probabilities. Okay, so this is the vocabulary in the literature usually. So when theta is set to 0, you have an elliptic equation here, and this is called the parabolic-elliptic model. And it may be decoupled, and I think you see it, that if you set this to 0, then you kind of have a Poisson equation here, and you can use the Green's function to decouple this and basically have only one equation, okay? However, when theta is strictly positive, so this is the doubly parabolic setting, then you have this strong coupling between the two equations, okay? So that you can't decouple them. And this is going to be our case today. So we are going to try we are going to derive the system through, in this framework, okay? Where you can't decouple the two equations, okay? So why this system is interesting is because well, it was designed to do so, but still. So this system may blow up in finite time, like depending on the parameters of the model. But it's not a surprise. It was really designed to model a beginning of an agglomeration. Okay, so it's a feature that is kind of desirable here. Okay, and so finite time blow up or a global existence. So this is the question that you ask yourself. And the finite time blow up, you kind of see it as an agglomeration. So some kind of agglomeration happens of your cells. Okay. And in the case where you can decouple, so when theta is 0, so when you're in the elliptic case, where you can really decouple and write only one equation, then this is very well understood. And basically, you have this threshold, it's very famous, 8 pi. And it basically tells you that, OK, you have to have some good initial data. But if your strength of attraction, so the sensitivity, is small, then you have global existence and there is no blow up. OK, but if the strength is large, of attraction, then you will have explosion in finite time. So you will have some kind of agglomeration. Okay, so that's in the case of parabolic elliptic. In the parabolic case, it's a bit more obscure because if I understood well, so in this problem, it was more or less easy to see this 8 pi and to see this part, so that there cannot exist a global solution in this case. Okay. But it was difficult to find existence up to 8 pi, and they needed to find a good functional inequality that will give the 8 pi. Okay, and here it's a bit reverse. So here, this was kind of extended. So the existence then was extended. The techniques were extended, but then the blow up was kind of hard to get. And we were searching for different results. So still, you have the 8 pi threshold for some. For global existence, and it's not really a real threshold. It's more like, okay, in some cases, for some class of initial data, you have global existence up to 8 pi. But then you can also, in a specific setting, if you don't have initial concentration, or if the initial concentration is very small, then you can find, so you need to kind of put in the game also theta as well, the parameter of the diffusion scales. And then you can basically go above 8 pi, so, but only in the cases where the concentration of the initial concentration of the chemical is small. Okay, so you can go even above, but for the global existence, but you need to have no chemical at the beginning, or very small chemical concentration at the beginning. Okay, and then very recently also we found in the literature some kind of explosion result where there is really a class of initial data for which there is the finite time blow up. And in this class, some energy of the initial data, I think, needs to be big or small, I'm not sure. So this is very recent, okay?
So, Milica, and is it this finite time blow up depends, how does it depend on the theta in this case?
In here? I can't remember, but it's not contradictory, okay? It's not like there is some gap between... I think here theta is maybe 1. So sometimes, that's not a... And it's more about the smallness of the initial data, or the initial data energy, okay? But I can't remember really exactly. Maybe theta is in there as well. I can't really... There is like a very big class of initial data that is identified, okay? So maybe a thing to remember is that these two things, like chi, which is the sensitivity, and this theta, which is the ratio of the diffusivities, are going to play a role, and that the initial data, so kind of like if it's very, very small, you should be able to find a theta for which, for any chi, like you give yourself a chi, and then you can find a theta, so the model is well defined. Okay. So this is the starting point, and then we would like to see like a particle system here behind this, or two particle systems, to kind of approximate from the probabilistic viewpoint this equation. Okay. So the first question you ask yourself, because you have this system, maybe I should have written the system quickly on the board. I think I took a chalk in my pocket. So just to So you have the diffusion, and then you have the drift, and here you have your theta. So here again it diffuses, it decays, and then it's produced. Okay? And then you have some initial data. Okay. So of course, if you look at the first equation, you see it as a Fokker-Planck equation, right? If you forget C, if you don't have the coupling, you see it as a Fokker-Planck equation, and you can say, well, a typical particle, okay, if n is infinity, a typical particle here would just be a Brownian motion with a drift, which is the gradient of the concentration, right? Like it would just be this, if C was given to you. Okay. But then on the other hand, C is not really given. C solves like this kind of equation where rho is the source, okay? So what kind of, like a strategy of decoupling that I proposed here earlier before this work was that we could just, for C, write a Duhamel form, okay? So you could write, so this is like some notational thing here, but for C, if I assume that C0 is 0, for example, and that lambda is 0, let's say, then C, you just see it as the integral of the heat kernel convolved with the source, right? More or less. Yes. And you need a good variance here. Okay. So this is basically what's written here, just with some notations, because there is many parameters. There's C0, there's theta, there's lambda, etc. But basically, this is what you see here. So you see how your heat kernel kind of transports the source. And so if you do so, and you kind of look at this together, it's a bit hybrid, but you can do that, at least formally, or informally. And then you could put this all together. You could say, well, I'd like this to be the C, okay? So I'm just going to take the gradient here, plug it there, and write what I have, okay? So we do that, and we come to a nonlinear process, okay? So a stochastic process where okay, you have some Brownian motion, you have some linear part, so you have some drift, but then you have another drift which depends on your law. Okay, so you need to impose kind of so the circle is very well done, so everything should match. So this rho should be the law of this process. Okay, so this all matches. So this is what happens here. So here you have your typical particle. So n is infinity, let's say. Your typical particle is kind of interacting with its law, okay? So that's the Mekin-Vlasov setting, so the nonlinearity. But then what happens here because of the parabolic coupling is that it doesn't just interact with its own law, it interacts with all of the past laws, okay? Because I did this basically, okay? So you have this past law dependence in the stochastic differential equation, okay? And then you have another inconvenience, and that is that your the way your typical particle interacts with the law is through the derivative of something, and derivative of something is basically the derivative if I take the gradient here. So it's the derivative of the heat kernel, okay? So it's the derivative of the heat kernel, and you need to integrate it in time. So it's as soon as you derive your Gaussian, you pick up a singularity there, okay? You pick up, well, we'll talk about it more, but like, of course, it's going to be the main problem. So you pick up something that's singular here, and you kind of need to define this integral. So there is kind of a singular interaction with the law, okay? But you could hope that the law lives in a good space and that you could like kind of smooth out the singularity because rho is very nice, okay? Although, okay, that's what you could hope on the level. So this is on the level n equals to infinity, okay? This is a typical particle in a cloud of infinitely many particles. Okay, and then you could discretize this, so to find your particle system. So you fix an n, and then you plug your empirical measure there, where there was the law, okay? And then you get this particle system. So again, some Brownian motion, some initial data, some linear part at the first read you could just set to 0. Okay, and then here is the interaction. So now you see that you have like a path-dependent interaction between your particles. Okay, they are like at each time each particle interacts with all the paths of all the other particles. Okay, so it's completely path dependent, and it's not a surprise. It's because there is this time basically that is introduced through the doubly parabolic coupling. Okay, so the second equation introduces memory in the first one. Okay, so you have here a strongly non-Markovian system. Okay. And then also, like now you can see the interaction, so 2 by 2 interaction with the path-dependent interaction. You see that basically the interaction is the whole this integral here, okay? So like this particle I at time s interacts with all the paths of all the other particles through this singular kernel now, so the derivative of a Gaussian with a complicated parameters, okay, but it's basically the derivative of the Gaussian. And now you see that basically you have a time singularity here in this integral, okay? So when I derived the Gaussian, I picked up a singularity in time, okay? Of course, I have this, like, of course, I have this x, okay, good. I have this x here, so it can eat a half here. So this is, but still, like, this is of the order 3/2 in time, and here you have a time integral. So there is a problem, okay? And the main problem is when 2 particles actually like collide, that they touch at the same time, okay? So it's not like, let's say that if this is 0, that's not such a big problem if it happens far away in the past. If you percute a past of another particle, so you're gonna, okay, like you're gonna have a 0 here, but if that happens far away in the time, that's not a problem. You're still gonna integrate. What is problematic is when u goes to s, so around s here, and 2 particles, so the 2 trajectories are colliding. In that case, like nothing can save you here in this interaction. In this, this exponential has no force anymore, and you have your singularity in time. Okay. So the problematic things, although this is a path-dependent interaction, the problematic thing is when we collide, okay? So because in that case, like the exponential thing here will not save us and will not help us to integrate in time here, okay? So it's a kind of a space-time interaction that's singular, okay? And so the first question I always get asked is like how singular this is. How big is this?
Sorry, in the interaction term, it's really xs minus xis minus xju, or is it at the same time?
No, it's not at the same time. Yes, exactly. So that's the whole thing, and it's really because here you interact with the path law. So when you plug the empirical measure, you get your s, let's say here, and your u for the other ones, okay? And it's just because of the memory that the second equation injects in the first one, okay? So it's really path dependent, and you can do nothing about it, okay? But the problems happen when we touch at the same time, okay? It's not a problem if we percuted the past of another particle, so like in the past. Okay, that's not, you see that kind of, it can be like, this is 0, but it's not a problem because it's far away in what's problematic is when we are approaching each other, so nothing here can help us integrate this kernel, okay? So then the singularity, like, the drift, let's say between 1 and 2, like the interaction between 1 and 2 at time s this is time integral, as you noticed. So the derivative of the kernel, which is the, okay, and then 1 and 2 different particles, okay, in different times, okay. So this is the interaction, okay, between 2 particles, but it's only problematic basically when xt1, let's say xs2 goes to 0, no, t, u. No, s. S and u goes to 0 as u goes to s. Okay, so when they start meeting, okay? And so you could like kind of ask yourself, so what's the order of singularity? If they meet, like, how does it explode in the distance of xt1 and xt2? And so, of course, now I'm doing like a reverse engineering, and I'm doing an inceptioning you to trust me that this is the good order of singularity. But this was like, we needed a lot of time to kind of prove that, but you'll see. So a very exaggerated situation to kind of see how singular this is, okay, is that if you suppose, but this is very, very exaggerated, probably this will never happen, okay, that in a period of time, okay, let's say that two particles behave like this. Okay, let's suppose this, okay, so that in a small period of time, basically there is this vector r, and the other this, like, we are always at the distance r of 1 and 2 are always like this for a small period of time. So in that case, if you look at their interaction here, okay, and you really like compute what happens. So now like here you have your r, the norm of r. Then like you could do this by hand, and you could see that this as r goes to 0. So as if they like are really approaching, then this behaves like 1 over the norm of r. Okay, so like that was kind of the idea is that this should kind of explode like xs1 over xs2. Okay, this that's the message that I wanted to give you. Okay, and this is exactly the order of singularity when theta is 0. Okay, if you put theta to 0, then the order of singularity is exactly this one. So we kind of, our mantra when we started this was, we kind of have to get this, okay? We kind of had to understand that even if it's path dependent, the problem is only at the same time, and how it explodes is basically of this order. That's kind of what we, what was the idea of how to proceed.
So Milica, but you had a double integral in time. I mean, you had like one in it.
Yeah.
Can't it be useful to have that as well?
Yeah. That's for me. That's more useful. Like at when n is infinity, it like smooths out. But now when n is fixed, now you have Dirac's, like so. But I agree with you. Like there is some kind of smoothing through the time integral. Okay, but all in all, like that smoothing kind of should give you this, and then you should integrate this. Okay, so at the end, you're still in a singular situation.
Okay, but integrated in S.
But this is not like when you do the D formulation, right? Your drift is gonna be this, right? Because there's two integrals, but one is just the trajectorial definition, and the other one is the interaction. Okay, so once I say that this is of the order 1 over the distance, I'm like back in a really very singular setting. Okay, but at least I got rid of the past dependence. That's the idea, to get rid of the past. Okay, so. Okay, so here is a small simulation, just to kind of convince you that there are pathologies with this system. So if you discretize it, and you just change the chi, so the sensitivity. So when chi is very large, like this is the initial data, it's just a uniform on a square, you see that some kind of agglomeration is kind of forming, okay? While when chi is small, you see that basically the particles are diffusing. Of course, you need to wait more time to see a really like a point agglomeration, okay? But this is very costly, and maybe, like, I don't want to spend a lot of time on this, but you've seen the non-Markovianity, you've seen the path-dependent interaction. It's very, very costly to simulate this, okay? Like, there is no way to Markovianize this in the Euler scheme. You really need to, like, take all the past, compute all your, like, sums, because you need to discretize here a Riemann integral. So you have like a double discretization. So here you need to discretize this guy, okay, in the Euler scheme. So everything you calculate in step k, when you go to k plus 1, you can just throw it in the bin and you need to recompute everything. So there is no way to Markovianize the simulation, okay? So it's very costly. And it's a completely different project just to have efficient simulations of this, okay? And of course, like, this can't help you because we haven't proved it yet. And you'll see that this, like, you can't prove this trajectorially. You can't prove this, like, you can prove this somehow, but not not really. So you can't like, all the quantities you compute, they're always, you have to forget them and recompute them. And so the time advances, you have a big matrix of positions, and it becomes really, really costly. Okay. Okay, so some things about the literature. So maybe I'll just mention here some papers that are directly related to the techniques of the proof, or like to the doubly parabolic. Okay. So in the doubly parabolic case, in dimension 1, I worked on this problem as well, and it's still singular, but it's less singular in dimension 1. But still it's singular because it's order 1 over t. And we got actually the existence for the particle system and the propagation of chaos using some kind of interesting Girsanov transforms. But this is totally impossible here, okay? It's impossible to kind of justify any kind of Girsanov transformation because this is too singular, and you should not expect that the particles like law is absolutely continuous to the law of independent Brownian motions, okay? Because the particles are attracting each other. And in dimension 1, actually, there is no explosion in finite time, so kind of like, so we could have went through with a Girsanov, okay? And some neat Girsanovs for the limit. In any dimension, there has been some work on this using two particle system discretization, so a bit different. Like you have your first one, which is just a particle that kind of follows the gradient of c. But for the second one, like you say, okay, these are Brownian motions that die, you kill them at some rate lambda, and then these particles produce them at rate 1, okay? And then you could define like two systems, let's say a red and a blue system. But then what you have a problem when you define the position of the red, let's say these are reds, because you need the gradient of the empirical measure, right? So you need to kind of regularize the empirical measure. You can't just take the gradient of Dirac's. So that's a bit of arbitrary, like you kind of need to mollify everything. So you have two systems, but like the first one has to be mollified, so you could take you have some local density. You can't just define a drift as the derivative of Dirac's, okay? So, but it's actually, it's very neat, and it's very satisfying because it's biologically it's more satisfying to see two systems. We here propose only one, and from the one system, we kind of recover everything, the C and the rho, okay? We recover them both, but at the limit. But we only have one particle system, okay? And of course, this can work in any dimension, and everything is smoother, and it is interesting actually to see it and to compare it. And then, of course, very closely related is when theta is 0, okay? So then you have the parabolic-elliptic equation. And in that case, you can have a normal Markovian system, right? And the difficulty is that basically, that's what like the rate of the interaction is of order 1 over the distance, okay? And it's attractive. So, like there is a competition between the Brownian and the drift that tries to put the particles together, and the Brownian tries to separate them, and you can see it on the system, and so it's not obvious that it's well posed, that it converges, but still they manage to get some results on it, actually a lot of results, and first up to not an optimal threshold, but then recently Johan also got the optimal threshold and much more things about this, okay? So it's very closely related because somehow, if I manage to perform this, okay, if I manage to somehow perform this Markovianization, I would be in this framework, and then I could like lean on their techniques, okay? But I would first need to understand the path-dependent interaction, okay? And kind of Markovianize it. So the main result is, well, very quickly, okay, is that the system does exist, and it does converge, but there is a threshold on which we can do that, okay? So we can define it and we can converge it up to a subsequence, of course. So it's a tightness consistency argument. And the main question is, how big is this threshold, okay? When we started working on this, I said I would be happy with any threshold because it's been many, many years I've been looking at this problem and even set it aside, etc. But then, of course, when you solve it and you get your threshold, you kind of want it to be better and better, right? So the expression from the threshold is very complicated, okay? But it's explicit. You can compute it with your initial data and everything. And if you optimize the conditions, these are kind of like thresholds we get. So if we were just put theta equal to 1, we get something that's yeah, something like this. So it's not 10 to the minus 10, but it's not 8 pi or something like that, okay? And if we start like going to 0 with theta, so we are kind of going towards the parabolic elliptic, so we get a bit better, but we don't get 8 pi, okay? We get pi. So something in our things, like something is not optimal in our computations, okay? And then if we increase theta, I told you, if you put C0 to 0, you should expect that you could find for each chi a good theta, okay? But for us, it's reverse, okay? Our threshold decreases. So this is where we see that it's like, because for us, nothing depends on the initial data, okay? So we see kind of that we kind of, here, we lose a little bit, okay? At least in the case C0 equals 0, at least in that case. In case when C0 is not small, then in the other works also the threshold behaves, it decreases, okay? But we can't see that because for us it doesn't depend on C0. Okay, so for the limit, so what happens is that at the limit we find some kind of measure solutions to the PDE, and these measure solutions are very weak, okay? It's a very weak notion of solution. The only thing we know for the limit is that it integrates basically our kernel, like if we tensorize it, okay? So that everything is well defined. But our limits are measures, okay? They're not densities. Even if we start with densities, we don't know how to prove that that propagates, okay? So they are very, very weak notions of measure valued solutions, slightly different than the ones that are in the other papers of PDEs. And it's very difficult to show uniqueness for such a notion of solution. So we basically have the weak form of the first equation with the time like integral already injected in it, something like that. And the only thing we know about the solution that it satisfies this. So we couldn't show uniqueness. So we don't have like the propagation of chaos. We just have tightness and consistency. We know that every weak limit is our solution, but we don't know that the limit is unique. Okay? At least not in this class of solutions. Okay? Okay. And so about the initial data, I didn't tell you, but the only thing we suppose is that the particles are exchangeable. We don't suppose, like, we can work with a singular initial, we can work with Dirac's as initial data. Okay? Okay. So the proof, I have a bit of time. So the strategy I kind of already told you is, well, you'll see that this is the key, but basically what you want in any kind of singular interaction in this kind of framework is to control the 2x2 interactions. You want to show that the 2x2 interactions are not that bad, okay? So you want to prove some kind of estimates of this form on your 2x2 interactions that are independent of n, and so a priori if you know how to do them, then the rest is fairly standard once you know how to control the 2x2 interactions, okay? So then you could regularize the interactions and kind of take limits, etc. But the main issue is always to control the 2x2 interaction, okay? And for us, so the idea was to show this kind of argument, so to perform a Markovianization of the system in order to attack now this 2x2 interaction. And rigorously, what we are able to prove is not something like this. This is impossible. Like if you take two continuous trajectories, you can't get this, okay? But what we prove is something like this. So up to an integral, up to like a power and an expectation, okay? This works, okay? It is of this order, okay? But it only works for a certain range of parameters here. So this is basically between 1 and 2, I think. But it's still good enough. If you know how to a priori control the interaction like this, like then you would win afterwards, okay? Because you would be in the case, the elliptic case, in which you already have techniques that are available, okay? So what we are rigorously able to prove is this. And once you have this, so this is just to convince you that the things can then go smoothly. If you have the Markovianization, this is basically the argument of the techniques that are available. It's just that then it would be easy kind of to control some negative moment of the interaction if we would have the Markovianization. So this is like the next step, let's say. So it's not important that for you to understand like these computations. It's not that quick to explain them. What it's important is that if I would know how to do this, then like this, I would be able to kind of repeat the parabolic-elliptic arguments, and every time I'm with the path-dependent interaction, I kind of use my estimates, and then I repeat their techniques. Okay, so more or less, like Markovianization is kind of the key. The rest then goes smoothly. So how to perform this Markovianization? So that's the only thing I would really like to explain. Okay, so the idea was that, okay, so there are 3 ingredients like to do this. You need a suitable Ito formula. So we work a priori on the particles, okay? So we suppose they are defined, then we work with them, then you can add an epsilon everywhere, and that works. You need a suitable Ito formula to kind of treat this, to kind of see the evolution in time of these kind of terms, okay? You need to find a convenient function in which you want to apply the Ito formula, so you can kind of control your terms. And at some point, we realized that when we were doing that, we needed a function inequality. So we kind of derived a nice function inequality that we didn't find in the literature when we were doing all this. Okay. So these 3 steps, I'll try to summarize them in the next, how much I have, 10 minutes, right?
Yeah, about 10. Yes.
About 10, okay. So I'll try just to tell you some ideas, okay. So you see all your terms are of this form. So you always have like the integral of the path, okay? And you always have basically a function of the current time and the previous times, okay? So you will want to know how this evolves in time. So you need a suitable Ito for that, okay? And a suitable Ito is of this form. This is not very difficult, everyone can do this. You just have to like do an Ito between S and T for 2 particles, so only on x1 by freezing the second one, and then, okay, integrate in time and do a Fubini, okay? So, like if you sit down and you do it, that's gonna work. But what you really see and what's really important is that this kind of interaction, like the forms of the integral, like path-dependent interaction we have, like basically, what's neat is that here the initial one is at the same time, okay? So when you have your suitable Ito formula, you see that there is one term, all the terms are path-dependent, except of the one when t is equal to s, okay, when you do the Ito here. So this is the term that you should kind of imagine that should give you this, okay? It should give you your present time interaction, okay? And all the other terms, what it should kind of happen, what you kind of expect to do, is that basically this one is nice and it doesn't play any role, and that these guys are of the same order, and that they are him, okay? They are kind of like mimicking your drift, okay? So if you are able to kind of find a good F, which would be of the sort that those terms are of the same order and they are of the order of the drift, and then you have this guy here, you could put this one on the left, and then you would kind of have some estimates, okay, on this. So the idea is really, with this suitable way of how these things move, is to find now a good F that would produce terms that you like, okay? And so we were really like looking, but basically here we were looking for a function that gives, like that solves this equal to this, okay, this side. So we produce basically a drift on the right-hand side, okay? And then when we get that, then we would like, okay, take the gradient and try to prove that this term dominates this one, okay, so that everything is of the same order. And then you would see that there is some kind of like, you need the key to be small, so for this to work. And when we were looking for that, it took us weeks and weeks and whatever, like we were so into like going for this one, and it didn't work at all. And then we said, okay, maybe we just not that good in in solving PDEs. So maybe we should find some f, something that resembles the drift, okay? So we are not really, like we don't really need to go for the gradient of g, okay? We could go for something that is an upper bound of the drift, still path-dependent. So we noticed that you could separate the time and space, so the interaction is basically like also of this order. So if you imagine that drift is not the gradient of the heat kernel, but it's like something that separates the time and space in such a nice way, okay? Then like you could try to work with that, okay? And this is what we did. So we kind of forgot grad g as the interaction. We just said, okay, let's work with, let's think that this is the drift, okay? And in that case, okay, we found a nice f, okay, that could have a nice properties. So like there is some lower bound on the part like where you have the Laplacian of f and dt, okay? And then there is some upper bound for the gradient. And now the game would just be to kind of try to show that when you integrate this term, when you see the Ito formula, this guy dominates this one, and that I'll show you now. Okay. So what happens if you plug this f, okay, in my Ito, you have something negative here, so I'm just going to forget it. You have this guy, which is the nice guy, it's him basically. So you put it on the left side. And what you would just want here is that, so these are the upper and the lower, like the lower and the upper bounds. You would just like basically to dominate this guy with this guy to have only one crucial term, okay? So you need some kind of a Holder inequality that could kind of compare. So there is no more gradient of g. There is like stuff that are of this form to some power, okay? So there is no time and space mixed, but there is like time and space separated like this. And if we would know, if we would have some kind of Holder inequality that could compare those terms, we would kind of like, okay, I'm putting like it's under the carpet a lot of computations, but kind of it's really crucial to be able to compare this kind of these guys, okay, which now play the role of the drift. And what happened is that at that time when we were doing those computations, so when we replaced the drift with this, with 3/2 here, we kind of figured out that if we had this function inequality, we would kind of, that will open all the doors, and we would be able to kind of compare all our terms. Everything would be in the nice order, like everything would go in a good way, okay? And what you see here is some kind of a Holder. So I have like this f, you should think about it as the distance between two particles, okay? And you should think like, you should see, we want to compare those kind of terms where like, we start with something like this and we always want to increase the power here and we need to pay something, okay? And f is positive. That's the only thing you know about it because it's the distance of two particles. And you want here a constant that of course does not depend on f, okay? Because like f is the distance between two particles. You don't want a random constant, okay? And of course you want best constant possible because every time I did, like when I replaced the drift with this, every time I'm losing, and I want a good chi. So that's where I'm losing my threshold. So we kind of, we found this and we were like, okay, we would need this and like how to get data, okay? And we found that this is actually true for our positive f. In the beginning, we didn't believe it. We thought that like, this is not true, so we're trying for a counterexample. And then we found it was true, but I have to say that we had to talk with many colleagues, and I have to thank Benoît Pertin and Vincent Calves, with whom we talked a lot about this. And at the end, we were convinced it's true, and that actually we found the optimal constant here. Okay. So once this kind of Holder is here, like then you could compare all your guys, okay, and you could. So now, of course, like it's difficult to see this very quickly, but I told you the drift is like of the order 3/2, so that's the drift. So now the drift, like you want it basically to be of order gamma. You want this term to be order, like to be dominated by this one. So you want to increase, so like gamma is larger than 3/2. So you do your functional inequality path, like here you have some residual, you have some constant, and you put it on a good thing. The same like for the other guy here, like you have another term here. You do your functional inequality, you increase the power, you pay something, you pay a constant, puff, you get something here. And what was really magical was that these exponents were conjugate, okay? So they actually, like, using the exchangeability, they really give you what you're looking for, okay? They really become this guy, okay? So it was really magical that all this kind of came into place and that they were compatible, okay? And of course, like then you need to work a little bit more, but at the end you can really prove this, okay? So I'm skipping that, but like once you kind of manage to compare your terms, if you suppose that chi is small, then you really, really, really can prove this directly. And the main ingredient was this, like this functional inequality.
Do you know why the two exponents are conjugate?
Do I know why they're? No, I don't.
Maybe there's some reason.
Well, they have to be conjugate because this has to be of the same order. Like, okay? Like I skipped the elliptic case, but in the elliptic case it's Markovian, so it's really of the same order. If you take your function f as like just the distance to the power alpha, and you derive those things and you have the interaction, everything comes into place without any holder, without any inequality, because they are really of the same order, because the Brownian and the drift are of the same order in dimension 2. Because you're in dimension 2 and the competition is fierce and it's of the same order. No one should win. The key should tell you who wins. So here it's kind of the same. There is this competition between the Laplacian and the drift, and they should be of the same order, okay? But we could have been not precise, and this could have not come into place, okay? So yeah, so at the end, maybe I stopped there, but just like tell you that at the end, like what was really crucial was to have this idea to get rid of the path-dependent interaction, and in doing so, we kind of realized that at some point we needed like a nice function inequality, and then the rest kind of went well. So I'll stop. So we can.
Thank you.
Other questions or comments?
So where does the restriction on the chi come from?
So two important places. When I compare all these guys and when I kind of put them on the same form, here there is a chi. And you see that they don't play in the same, so there is a lower bound here. And when you collect them together, when you do your function inequality, here you have like one dominated term with some constant minus another constant that depends on chi. And you want that to be positive. So that's one place where you have the restriction, because this goes on the left. So in order to just obtain the Markovianization, you kind of need, when you collect the terms, you kind of need something to be small. So like, and chi plays in that opposite side, okay? But then that's the first place when you need chi. The other place is once you obtain the Markovianization, you come back to the elliptic place, and here also. So you kind of use this technique twice. Once to obtain the Markovianization, the second time, once it's Markovian, to like deal with the interaction. So you have like a very nonlinear and ugly condition on chi.
But the second restriction is more linked to the restriction you have in the elliptic test. Right?
Yes, exactly. Yeah. But first you have this one. So that's why I told you like the form is explicit, but it's not nice. Like it depends on many things here on the initial data, on a lot of things. But basically, yeah, you pay twice. Yeah.
Okay. So since we are running already a little bit short on time, I suggest we save other questions for the break. So thanks again for a beautiful talk.